Welcome to the Deep Dive. We're the show that, peels back the curtain on the tech we use all the time.
Yeah.
And today, we're diving into something almost everyone touches daily, Google Maps. Think about it. You need directions, you pull out your phone, bam. Instantly, there's a route, an ETA, even traffic. It really feels like magic, doesn't it? But how? How does it actually know all that stuff?
Yeah, it does feel like magic sometimes, but definitely not. This deep dive, it's really our journey behind that simple screen. We're going to unpack this, well, incredibly complex system. There's data collection, AI, and maybe surprisingly, a lot of human input, too. It all works together.
Right. And for you listening, understanding this isn't just trivia, it's about those aha moments with a tool you rely on constantly. It's kind of a shortcut, really, to being genuinely clued in on how our digital world maps the physical one.
Yeah.
So where do we even start? It seems massive.
It is huge.
Yeah.
But you got to start somewhere, right?
Yeah.
And that starting point, the real foundation, is imagery, the visual backbone.
Imagery. Okay, so literally just looking at the world.
Pretty much.
And that has to start high up, I'm guessing, like satellites and planes?
Absolutely. Yeah, Google Maps kicks off by using satellite and aerial images.
Mm.
That big picture view is, well, crucial. It's how they first spot roads, buildings, addresses, businesses, even things like speed limits sometimes. They get these high-res images from companies like Digital Globe, Skybox. Google licenses them and pulls it all together.
Wow. It's wild to think maps start as space photos. I remember when Google first added satellite views back in '05.
Oh, yeah.
Everyone immediately looked up their own house. It was mind-blowing then.
Definitely a game changer.
Yeah.
And those images, they get updated regularly. Some are super recent, like 2 weeks old. None are older than 3 years,
Yeah.
generally. But that bird's eye view isn't enough on its own. They need to get down to the ground level.
Street view.
Exactly. That's where Street View comes in.
That really changed things for exploring places online. How long has that been around? And the scale, how much have they captured?
Street View launched back in 2007, and since then, over 170 billion images from 87 countries. It's staggering.
170 billion? How do
Yeah.
they even get all that?
Well, they have a whole fleet. The most common thing you see is the Street View car, right? With the camera rig on top. Those cars alone have mapped over 10 million miles. And many newer ones have LiDAR sensors, too.
LiDAR, L-I-D-A-R.
Yeah, light detection and ranging. It uses lasers to measure distance, plus GPS for location. Really precise stuff.
Okay, but cars, they can't go everywhere, can they? Like narrow old city streets or hiking trails?
Right, exactly. And that's where the Trekker is key. It's basically a portable camera system. They can wear it as a backpack, mount it on trucks, snowmobiles, motorbikes, you name it. It lets them get into places cars just can't. Think, like Machu Picchu.
Wow.
And this is where it gets kind of fun. They really adapt. They put cameras on bikes,
Yeah.
sometimes even camels.
Camel.
Seriously. Camels, divers, even astronauts. And the tech has shrunk, too. The original camera was like 500 pounds.
Whoa.
Now there's a new one that's just 15 pounds, powered by a phone,
Mm.
detachable. Much easier to stick on a camel, I guess.
That's incredible. From deserts to space stations, mapping everything. Okay, so they collect this mountain of images. How does it become the smooth 3D thing we navigate? It must be like a crazy jigsaw puzzle.
It is, yeah. A very complex one. They gather the images carefully, thinking about weather, how many people are around. Then they have to align everything. They use GPS, speed sensors, direction data from the car, basically rebuild the car's exact path to line up the photos.
Okay.
And for those 360 views, the cameras overlap slightly. Then special software stitches them together. It uses algorithms to smooth out the seams, make the transitions look natural.
And the 3D feeling, like you're actually there.
That comes from the lasers, the LiDAR. They bounce off surfaces. How fast the light comes back tells Google the distance to buildings, objects. That lets them build a 3D model of the environment. It's how they make sure you see the right picture as you move down the street.
Okay, that makes sense.
And importantly, this imagery isn't just for looking at. It's constantly used to update the map itself, spotting new shops, maybe a new stop sign, changes in traffic lights, comparing the new images to the old map data.
So the pictures build the visual world and also help keep the map data fresh. But just seeing isn't enough, right? You need to know what's there. Addresses, businesses, this is the data tapestry part.
Exactly, that's a good way to think of it. It's woven from different threads. One huge thread is authoritative data. Google pulls in info from over 1,000 verified sources worldwide. Think big government agencies like the U.S. Geological Survey or Mexico's National Institute of Statistics and Geography.
Official sources, okay.
And they've even built a tool now to make it easier for local governments to directly upload info about new roads, new addresses.
So governments are a big piece, but it can't all be official data, can it? I feel like there has to be a human touch in there somewhere.
Oh, absolutely. There's a whole global data operations team at Google. These are the folks checking the data sources, fixing errors, and really importantly, training the machine learning models. We'll get more into that.
Okay.
And then there's the community, huge part. Local guides, regular users, anyone using that send feedback button.
So reporting mistakes or adding places?
Exactly. That crowdsourced info gets reviewed, and if they're confident it's accurate, it gets published to the map.
So real people, local experts, are constantly refining it. But the world changes so fast, surely they need machines to keep up.
You're spot on. It would be impossible otherwise. Machine learning is crucial for automating a lot of this or keeping it accurate.
How does that work? Like, what's an example?
Mapping building outlines is a great one. Early algorithms, they just made these sort of fuzzy buildings, blobs, really.
Right, I remember those vague shapes.
Not just ugly, but not very useful, right?
Yeah.
Especially for, say, emergency services or just finding the right door. So the data operations team, the humans, they manually traced lots of building outlines. Lots and lots. They basically taught the algorithms, this is what a building edge looks like. This is a proper shape.
So human training for the AI.
Precisely. And it worked incredibly well. That technique let Google map as many buildings in just 1 year as they had in the previous 10 years.
Wow, 10 times faster. That's a massive leap.
Huge leap. It shows that combo of human guidance and machine scale.
Okay, so we've got how Maps sees the world satellite, Street View, and how it builds its knowledge with data and AI. But a static map is one thing. The real power often feels like it's in the movement, right? The traffic, the routes. How does it get the pulse of the world?
That's the next big piece, yeah. And it's evolved quite a bit. Early on, Google Maps did rely on fixed sensors, those sensors and cameras on highways, run by government agencies or private companies, laser radar, infrared stuff.
I remember seeing those little boxes on gantries.
Exactly. But that method, pretty much obsolete for Google Maps now.
Oh, really? So they don't use those anymore. What's the secret sauce for live traffic then?
The secret sauce is crowdsourcing. It's been the main method since about 2009. Think about it. If you're using Google Maps for navigation and your location services are on,
Which they usually are.
right, your phone sends these little anonymous bits of data back to Google, basically your speed.
My phone is telling Google how fast I'm going.
Anonymously? Yes.
Oh.
Your phone becomes a tiny anonymous traffic sensor in this massive network.
Huh. That's actually really clever and slightly creepy.
Huh. Well, it's anonymized, but yeah, it's incredibly clever. Google combines data from millions and millions of phones on the road, processes it constantly, and sends it back out as those real-time traffic colors you see: green, orange, red.
And because so many people use Android and Google Maps?
Exactly. They have a colossal advantage. Something like 41% of internet users worldwide use Google Maps. Over 1 billion monthly users. In the US, it's like 67% of smartphone users trusting Google for navigation. That's 6 times the next competitor.
That sheer volume of data must give them incredible accuracy, almost unfair.
It's a huge competitive moat, absolutely.
Okay, so that explains current traffic. But Maps often predicts jams before they happen, right? Or gives you that ETA that accounts for future traffic.
Yeah.
How does it predict the future?
Right, that's where AI and deep learning really flex their muscles. First, Google Maps analyzes historical traffic patterns. It knows, for example, that a specific freeway, say the 280 in California, typically flows at 65 miles per hour at 6 a.m., but slows to maybe 15 or 20 miles per hour in the afternoon commute.
Yeah.
It has years of this data. So it combines that historical knowledge with the live crowdsourced data using machine learning to make predictions.
So it's layering history on top of the real-time picture.
Exactly. But it gets even more sophisticated. Google partnered with DeepMind, that's Alphabet's AI research lab.
Oh yeah, DeepMind. They do cutting-edge AI stuff.
They do. And they developed this machine learning model using something called graph neural networks, GNNs. It significantly cut down inaccurate ETAs in major cities: Berlin, Jakarta, São Paulo, Sydney, Tokyo, DC. And the really cool part, this GNN approach helps predict slowdowns before they even begin.
Whoa. Predicting traffic jams before they form. That's genuinely predictive, not just reactive. That's the aha moment right there.
It is. It's a big shift. Getting ahead of the jam, not just navigating through it once it's happened.
But traffic isn't always predictable based on history, right? What about huge, sudden shifts like the pandemic lockdowns? Traffic vanished overnight.
Great point. Worldwide traffic dropped by like 50% almost instantly in some places.
How did the prediction models handle that?
They had to make the models more agile. Google updated them to automatically give much more weight to very recent history, like the last 2 to 4 weeks,
Yeah.
and basically ignore older patterns when things change dramatically.
So it adapted quickly to the new normal.
Yeah, it had to. And there's another piece that helps with sudden events, accidents, things like that. The Waze acquisition back in 2013.
Ah, right, Waze. That cost Google, what, like $2 billion?
Around that, yeah. A strategic buy. Because Waze is all about users reporting things in real time.
Right, potholes, police traps, accidents.
Exactly. Accidents, debris on the road, major jams. Google Maps integrates those real-time Waze reports. That gives it priceless, immediate knowledge about incidents that mess up normal traffic flow, allowing it to adjust ETAs and routes on the fly.
Okay, so we have the real-time data, the historical patterns, the AI predictions, the Waze incident reports. It's a lot. Once Maps has all that,
Yeah.
how does it pick the best route for me right now? Is it just basic computer science, shortest path stuff?
It starts there, yeah. At the core, it uses algorithms you might learn in computer science. Dijkstra's algorithm is a classic one for finding the shortest path in a network.
Yeah.
And also the A-search algorithm, A-star, which is like Dijkstra's, but often faster because it uses estimations heuristics to guide its search more efficiently.
Okay, Dijkstra, A-star. But wait, if every road junction is a point on this giant map, calculating a route from, say, London to Lisbon, wouldn't that take ages? Even with A-star, the number of possible paths must be astronomical.
That's the key question. And you're right, a brute force calculation on the entire global road network would be way too slow. This is where, as one source nicely put it, Google has to cheat like crazy.
Cheat like crazy. I like the sound of that. What are the cheats?
Okay, first big one. Pre-computing routes. For long journeys, they don't calculate every single turn from scratch. They have massive lookup tables, basically, with known optimal routes between major points or segments of routes. It's like dynamic programming in action. The algorithm finds the best way to get onto one of these pre-calculated superhighways from your start and off again near your end and connects the dots.
Ah, okay. So it's like it knows the best way to get on the M1, drives the pre-calculated M1 bit, then figures out the local roads at the other end.
Pretty much, yeah. It breaks the problem down. Second cheat. Hierarchy. They treat the map hierarchically. Big motorways connect regions, main roads connect towns, local streets connect neighborhoods. For a local trip, it doesn't even consider roads on the other side of the country. It narrows the search space dramatically.
That makes total sense. Don't look for paths through irrelevant areas.
Exactly. And the third big one, caching. Lots and lots of caching. It remembers previous route calculations, distances between common points. If someone just asks for a similar route or part of your route is common, it reuses that stored information instead of recalculating.
So pre-computing, hierarchy, and caching, it's all about avoiding doing the full mind-boggling calculation every single time.
You got it. And it means the goal isn't always the absolute mathematically proven shortest path, like that famous traveling salesman problem, which is super hard to solve perfectly for many cities.
Right, finding the single most efficient route, visiting multiple points.
Yeah. The goal here is to find a very, very good path, extremely quickly, that works well for the user. Practicality beats theoretical perfection.
A good enough answer fast is better than a perfect answer that takes minutes. Okay, I get it. So that covers the outdoors pretty comprehensively. But what about indoors? Hospitals, airports, huge shopping malls. We still get lost. Is Google Maps tackling indoor navigation, and how? GPS doesn't work well inside, right?
It doesn't, no. That lack of reliable satellite signal indoors is the big hurdle. But yes, they are working on it, and there's definitely demand. One approach involves getting digital floor plans of buildings, often from CAD files, the blueprints architects use, and overlaying them onto the map grid using Google's API.
Okay, so a digital map layer for inside the building.
Right. And then rooms, hallways, elevators, stairs. They become nodes in an indoor graph. Dijkstra's algorithm, or similar, can then find the shortest path between, say, the entrance and a specific shop or gate using precise coordinates, geocodes.
But how does my phone know where I am on that indoor map to start the navigation if GPS is out?
That's the tricky part. Indoor localization. A key technique is Wi-Fi fingerprinting, sometimes called RSS fingerprinting.
Wi-Fi fingerprinting, how does that work?
It's usually a two-step process. First, someone has to go through the building in a training phase. They walk around and record the signal strength of all the different Wi-Fi networks they can detect at many, many specific points, maybe every meter or so. This builds a detailed radio map of the building.
Okay, mapping the Wi-Fi signals everywhere. And the second step.
That's the online phase.
Oh,
When you're inside, your phone scans the Wi-Fi signals it can currently see and their strengths. It then compares that current fingerprint to the pre-recorded radio map. By finding the closest match on the map, it can figure out or infer your location within the building.
wow. So it uses the existing Wi-Fi infrastructure.
Exactly. And the cool thing is research shows this can get accuracy down to maybe 1.5 meters just using the standard Wi-Fi hardware already in your smartphone. No special extra gadgets needed.
That's pretty accurate. Good enough to find the right store or hospital wing. That could be huge.
It really could be. Makes indoor spaces much easier to navigate.
Okay, this is all incredibly powerful tech. Mapping the outside, predicting traffic, navigating the inside. But it relies on collecting so much data about where we are, where we're going. This brings up the inevitable privacy question, doesn't it? It feels like a constant trade-off. Amazing convenience versus giving up control over our data.
It's absolutely the core tension. Google Maps undeniably collects vast amounts of data, GPS coordinates, routes, sensor readings from your phone. However, Google is pretty clear on how they handle navigation data specifically. They state that the route you took, your speed along it, the data is tied to a temporary secure identifier that resets regularly. Crucially, they say it's not linked directly to your personal Google account. So they argue they can't just look up what route did John Doe take yesterday.
Okay, so the actual driving path isn't tied to my name or email. That's somewhat reassuring. What about searches I do in Maps, like searching for a specific address or business?
That's different. Yes, search history, or maybe ads you see within Maps, might be linked to your Google account, depending on your settings. But for the aggregate data used for things like traffic or finding busy times for places, they use techniques like differential privacy.
Differential privacy. What's that in simple terms?
Think of it like adding statistical noise to the data. It allows Google to see the big picture a traffic jam is forming. This restaurant is usually busy now from the data of millions of users, but makes it mathematically very difficult, ideally impossible, to trace specific patterns back to any single individual.
So they get the crowd's wisdom without knowing exactly what each person in the crowd did?
That's the goal, yes. They also say navigation data is deleted after it's used for its immediate purpose, like traffic analysis, and that map corrections aren't linked back to user accounts either.
Okay, that sounds like they've thought about it. But what control do I have as a user? Can I limit things?
You do have controls.
Oh.
One interesting one is for Street View. If you see your house and you're uncomfortable with it being visible, you can use the Report a Problem link on the Street View image and request to have your house or property blurred.
Oh, really? You can actually get your house blurred out.
Yes. They process these requests. It's available in major U.S. areas, California, New York, Florida, Milwaukee, and countries like Australia and Canada, too. It addresses that specific concern about, potential intruders casing places.
That's actually a really practical control. Good to know. What about location tracking overall?
You control the main location permissions for the Google Maps app on your phone. You could usually set it to allow all the time, allow only while using the app, ask every time, or don't allow.
Right, the standard phone permissions.
Exactly. Of course, if you choose don't allow, then real-time features like navigation won't work. And beyond that, you can manage ad settings in Google's My Ad Center and review your saved activity, including map searches in My Google activity, and delete things if you want.
So they are levers you can pull, even if the default is pretty data hungry for the features to work.
Right. It's about understanding the trade-offs and using the controls available.
Wow. Okay, so we've gone from satellites and street view cars through crowdsourced traffic and AI predictions, algorithms cheating like crazy, indoor Wi-Fi mapping. It's really clear that Google Maps is so much more than just, well, a map. It's like this living, breathing, digital copy of our world, constantly learning and updating.
It truly is an incredible feat of engineering, data science, and coordination. This deep dive, hopefully, has shown some of that hidden complexity behind this simple screen. It gives you, a much richer perspective on this tool that's become so integrated into our daily lives.
Absolutely. And looking ahead, with maps getting better and better at modeling, predicting, even giving us these immersive views, it makes you wonder, what's next? What new ways of exploring or connecting will this enable? And, maybe more importantly, what new questions does it raise about our relationship with all this data in a world that's becoming mapped in ever finer detail? Something to think about.